Hello, welcome back to the volume section of the calculus tutorial. This will be using washers as your method for finding volumes. Okay, so in your previous section we had things like this, to where you were given that area, and this is your axis of rotation, and you used a series of disks that were rotated around this way, to where if your axis of rotation is here, then it was a series of disks that were rotated around that way. So it would be a series of almost like coins, to where they would all stack up right next to one another like so, and they would calculate your area. Now, for washers, you would use the situation that would inspire using washers would be something to where, instead of like a full volume that we were used to with the disks, you would be given something like this, where your area is the area between y is equal to root x and y is equal to x. Is like, those are the two lines that form that area. And unlike with disks, you're not able to draw out a full box here, like to represent half of the disk. Is that you can't draw that all the way from the top of this y is equal to root x curve all the way down to your axis of rotation here. And that creates quite an issue, because instead of having just a bunch of just really nice circles of just different stacked radii, you get a bunch of washers, which is where the name comes from. Is that you have a series of shapes stacked on top of one another that are going to be a circle with a cutaway area in the center. That this is your axis of rotation, and then this is all the area that you're accounting for that you'll have to be adding up to get your overall integral volume. And so in the case of washers, instead of it being a integral from a to b of, like you would for disks, instead of it being this, to where it's just one area, that's just giving you just a circle over the course of a to b, which gives you volume. But in the case of washers, you get the integral from a to b of the pi r squared. Like, this is the outer radius. So let's draw another washer. This is the outer radius. Here is the longer line. And then your inner radius is lowercase r. And that's going to be we're going to be calculating that outer area and then subtracting this smaller inside negative space area from that area. So you get pi r squared, and then you subtract the pi lowercase r squared to get the sum of your areas. And that'll, as the integral will be it'll be summing up all of these infinitely thin slices of washers, while each one of them is being calculated as like that radius is being subtracted at each step. It'll make more sense once I change this r value, and we started off with the upper curve being y is equal to root x, and the lower curve is y is equal to x. And so in the case of this example, our bigger R is y is equal to root x, and then our lowercase r is y is equal to x. So this, you just plug y is equal to root x in for capital R, and then y is equal to x for lowercase r, which just gets you to be pi root x squared minus pi x squared. And then that's you just take that as a normal integral, and it would give you, it's pretty much exactly the same as the disks, except for you have to account for this right here. You have to account for that negative space. And it's solved it's set up and solved in the same way as disks were. Um, so that pretty well covers the lesson part of the disk of the washer section of the calculus tutorial. So I should be moving on just to an example here next. To a full example here next, using where I actually will solve for the A and B interval and probably use a more complex example than just root x and